I can trace this from other layers, locations as well, and so can you, depends on what you've got. You can do this from the VFS layer, that's fine. Syscall layer is fine if you can filter on the file system, file descriptors. Application layer is fine as well, and you may just code this into your application, that's fine as well. The application may have, like, I've looked at MySQL a lot, and it has my read and my write and OS file read and OS file write. You just add the statistics there. And I think they've been adding them with the performance interface, performance schema. I did this with System Tab as well on Linux, and I targeted the VFS layer, VFS read to VFS read return, and I got the file system type, just dug it out of the kernel. And so that's showing ext4 latency, which is actually what's affecting your application, not what the disks are doing. What the disks are doing can affect the application. You can get strong correlations. But here, as I went through all those reasons why that may not work so well. And I put a warning because I have been using System Tab on Ubuntu and CentOS, and I have crashed my system many times. People tell me it's better on Red Hat Enterprise Linux. I have not used it enough to, for sure. File system latency is so useful. We did put it into Cloud Analytics at Joyent. So this screenshot actually shows severe outliers. So file system I/O that's taking up to 5 seconds. 5 seconds for a file system I/O. It's really, really bad. And of course, once we create tools like this, the customers run them and send us screenshots. So, oh yes, that is really bad. And there's nothing we can say because it's actually hurting. It's synchronous to the application.
It's nice that there are these tools in Cloud Analytics, but wondering why we don't have better information in ZFS stat. I think it's ZFS IO stat, or I can't remember if it's stat or IO stat, built in to have those numbers there.
So, so ZFS IOStat does have, I'm used to saying ZFS these days. It gives you various high-level statistics. The ZFS team are all familiar with DTrace, and this is a problem that is not too hard to do from the VFS layer or the ZFS. It's the VFS to ZFS interface, and so far it hasn't been a huge need. If there was a huge need for it, then we could do it we could roll it into ZFS, but it is something that DTrace is quite good at alone. And usually on systems that have ZFS, they have DTrace as well. But you're right, it's any of these ideas that I've been presenting, if they're that important, you can roll them into your own tools. Just add statistics. You don't need DTrace, it's not about DTrace, it's about ideas and concepts and tools. Just as a different type of file system heat map, this one was very surprising. I caught that from Oracle ZFS Storage Appliance. This is showing NFS latency. NFS is a file system type, and it was caused by a pool of disks where not entirely sure why you have, I know why some lines are moving up and some lines are moving down. It's because it's a mirrored pool of disks, and you have each side of the mirror. One has increasing latency, while one has decreasing latency. What actually seeds the latency over time is really difficult to explain. It is a single-threaded synchronous write workload to a pool of mirrored disks. Very interesting file system latency. This explains something else, not just that file system latency is interesting, but looking at the full distribution as a heat map is also very interesting and useful. So for disk summary, IOStat can be pretty misleading. We created some new tools and metrics. Latency visualization is great. The last one I've got is just a network problem. TCP sins queue in kernel until they're accepted. The queue length is the TCP listen backlog. You may have been down this road before. You can set that in listen. The operating system will have some sort of limit. On SmartOS, it's this thing called TCP conrec max queue, which is 128 by default. It's often 128 in other operating systems. What happens if the queue remains full? Queue remains full. This is the TCP accept queue, and another SYN arrives, and it remains full because your application is busy doing work. Well, the packet gets dropped by the kernel, and a counter is bumped. So on this operating system, it's TCP listen drop, and that's actually happened a lot for this guy. So it's pretty high. The remote host waits for the transmit interval and then 1 or 3 seconds and then sends a transmit. How do we know if we're close to dropping? We know when we've dropped because when that counter gets bumped. How can I check my data center or my cloud and know how full the queue is right now? Simple task for DTrace to go into the, well, DTrace and nothing DTrace and networking is usually simple until after the TCP provider. But, so I've written this just as an example tool. When you run it, it will print a line of output for drop events if they occur. And when you hit, and it'll tell you the process ID that had it. When you hit Control-C, it then gives you the summary. It's showing the distribution of the queue length inside the kernel. And so the larger distribution there, process ID 11504. Max queue is showing me the in effect queue parameter, queue length. And most of the time it was 0, but it did make it all the way up to 128. And there were 34 instances where it hit 128. And at the bottom it shows there were 34 drops. Quick way to find out the length of the queue. And we haven't done this as a heat map yet, but it's something we want to do as a heat map so that you have that early warning. More details can be fetched as needed. So TCP listen drop prints out the source IP, destination IP, ports, so that you can see who's being dropped inside the kernel. This is useful if you're doing it via dynamic tracing because you can just trace the drop code path. You don't need to pay the overhead of sniffing all packets. And so you're not doing all the send and receives, you're just doing the kernel drops. And so this is the sort of thing I'm totally comfortable leaving running 24/7 by 365 on every machine in the cloud so that I can get information on those drop packets. Just as an example of what the code looked like from TCP listen drop, I'm going into the kernel, TCP input listener, I'm recording a message block buffer, and then I'm casting it as the IP header type and TCP header type, printing out details if you hit the TCP listen drop part of SNMP mid. That's using an unstable FPT interface from the FPT provider, but we did create a stable TCP provider, now exists, making some tasks easier, but not that one. So just to summarize that problem, for TCP, there are many counters that are available. If you do net sum minus s, there's a lot. They're system-wide integers. If you want to drill into more detail, and there's many times I've had to do this, dynamic tracing is one way to do that. And you can pull out, another way of course is to run TCP dump or snoop and capture every packet. Of course that has overhead. If I'm able to do dynamic tracing of the kernel, I can pull out kernel state that you can't see on the wire, and that can be pretty interesting. So as a recap of the data problems I showed, I had 2 problems of scalability, which is especially important for the cloud, where CPUs utilization, I used that heat map, and then the flame graphs for doing profiles of data. And then I had problems of observability and metrics. I deliberately put the data stuff first because by the time I got to the theory, a lot of the points may be self-evident and I really don't need to spell them out. So this is actually very quick. The goals for performance analysis is capacity planning and issue analysis. I spend most of my time on issue analysis, all of my time on issue analysis. For issue analysis, step 1 is there a problem? And step 2 is which subsystem or team is responsible. It's difficult to get past these steps without reliable metrics. We need to reliably say yes to the problem. We need to reliably say yes, that problem is in libumap, it's in the operating system allocator. Or yes, that problem is with the disks, it's not with the application or with the file system. For this problem space that we're in, some myths that I run into is that vendors provide good metrics with good coverage. Your mileage will vary. Sometimes they do, sometimes they don't. There's a lot of statistics that have been added, especially to the operating system, so that the engineer can debug their own code. I've been guilty of that when I worked as a kernel engineer. The problem is the line graph though. Well, there's other visualizations that can help a lot as well. In reality, metrics can be wrong, incomplete, misleading, requiring time and expertise to interpret. Line graphs can hide issues. Cloud computing confuses matters further when you're hiding metrics from neighbors, and they want to know what the neighbors are doing, and throttling performance due to invisible neighbors. Example problems I covered, included understanding utilization across a lot of CPUs, using disk metrics to explain application performance, and then a lack of metrics, which I see all the time, where I need custom metrics to really confidently nail an issue, send the other teams home, give it to the right person. Some of the example tools I went through, and if I had more time, I'd go through more tools, but I picked these so that they were across the board: CPU, memory, disk, network. I did the device utilization heat maps for CPUs, flame graphs for CPU profiling, and so on. And some really cool ones are like the heat growth for stack back traces is very useful. The file system latency tracing, ZFS slower, proving to be very useful. Digging into TCP and getting kernel state, very useful. Key concepts, again, if they're not already obvious. Heat maps are great for device utilization and latency as well. Flame graphs are pretty new, but we're finding them very useful. Custom metrics are often necessary, especially latency-based for issue analysis. If coding them isn't practical or timely, you can use dynamic tracing if that's available. That's what I tend to do a lot. And in cloud computing, providing observability is something that we believe in at Joyent, so that customers can see at least what the problem isn't. They'll tend to blame what they can't see, and to develop new metrics for resource control effects. A lot of the examples I went through were DTrace. Not a DTrace talk, I just wanted to show ideas, problems for cloud computing, and to finish DTrace, in the SmartOS cloud environment, the compute node or global zone can DTrace everything, except for the internals of KVM guests that are running Linux or Windows. You have a limited view, like resource I/O and some MMU events. Smart machines, that's what you get if you're a customer of the cloud. You can see yourself, syscalls, profile yourself, appeared in USDT providers. However, Cloud Analytics lets you extend your observability. That's part of why we're doing that, so you can see things you normally can't see. The last thing I want to say about performance is the more you know, the more you don't. And hopefully in the last hour I've turned some unknown unknowns into known unknowns. Thank you very much. The question is aggregations over multiple servers from DTrace. That's exactly what we're doing at Joyent with Cloud Analytics. And so you can look at this in real time, and I can demo it. We've got the code so that you can create a DTrace instrumentation, and it will talk to all the compute nodes. There might be 300 of them, and then we'll regularly pull a message back. Dave Pacheco, who's the lead engineer, did a good presentation at OSCON on it, talked about all the internals for this, uses AMQP.
Are there any problems that you solved because of that you wouldn't have otherwise?
Problems solved because of the wide scale?
More frequent.
Yes, it's doing things like the CPU utilization. It's just so quickly to find out that there are CPUs maxed out across the whole cloud, and there's some things I do check that from time to time. With the 5-second file system I/O that I had on a screenshot that I didn't explain, this is an example where doing DTrace across a whole cloud and presenting it out was that it ended up being a problem in the Dell PERC RAID controller. The way it was doing, there was a few effects, and one of them was the cache flush interval. But we suspected that a subset of our servers were being affected by this, and a telltale sign would be that they would have file system latency beyond 1 second. So I just brought up the file system latency heat map and then clicked on those spots. It's like, these are the guys that need their PERC controller tuned. So we're able to go and tune them and bring those latencies down. And so it is pretty new, actually, and I want to get more examples on my blog, which is there. One example I did have for cloud computing was on observer.inno.de, where they had a latency induced by a proxy, a web proxy, not the actual application. And so we used Cloud Analytics because it could look at Node.js request latency, and we're able to compare it very quickly there as well. So having DTrace across the cloud is pretty useful. Having it in a GUI is pretty useful. Not everyone is like me who enjoys writing 20-line, 30-line scripts all the time. It's just faster to click on things and to draw down analysis that way.